Reality itself might be a beautiful illusion. We are about to explore 30 cosmic paradoxes that shatter everything you think you know, from black holes that erase information to particles that communicate instantly across the universe. By the end of this journey, you will see the cosmos through a completely new lens. How can a cat be both alive and dead? And why does the night sky remain dark in an infinite universe? These are not just thought experiments, they are cracks in the foundation of physics, revealing a truth far stranger than fiction. What does it truly mean for something to be real? Enrico Fermi's simple lunchtime question echoes through the decades, a whisper that grows louder the more we learn. Where is everybody? He captured a profound cosmic contradiction. Our universe is unimaginably vast, with billions of galaxies, each containing billions of stars, most likely orbited by even more planets. The numbers alone suggest a cosmos overflowing with life. The silence we hear, then, is not just an absence of sound. It is a screaming paradox. The mathematics of probability insists the galaxy should be a bustling metropolis of interstellar civilizations, with ships cruising between stars and the radio waves buzzing with a million different conversations. Yet when we point our telescopes and listen with our most sensitive instruments, we are met with a deep, unnerving quiet. This is the great silence, and it forces us to consider possibilities that are as fascinating as they are frightening. One leading idea is the great filter. This is the notion that at some point between the emergence of life and the dawn of a galaxy-spanning civilization, a wall appears. It could be that the step from simple single-celled life to complex organisms is almost impossibly rare, a fluke that happened here but almost nowhere else. Or perhaps the filter lies ahead of us. Maybe every advanced civilization eventually creates the technology that leads to its own destruction, whether through climate catastrophe, engineered viruses, or artificial intelligence. The silence would then be a grave warning. Other theories are less dire but equally mind-bending. The zoo hypothesis suggests we are being intentionally left alone, observed from a distance like animals in a cosmic wildlife preserve. Or perhaps we are simply too primitive, our technology too basic, to perceive the complex communications already flowing around us. The universe might be full of life, but we are like a person in a dark room, unaware of the city lights just outside the window. Are we the first intelligent species to arise, pioneers in a young cosmos? Or are we the last, arriving after the party is already over? The Fermi Paradox offers no easy answers, only a mirror reflecting our deepest questions about life, intelligence, and our own lonely place in the grand scheme of things. That profound silence from the cosmos is a paradox of scale, but another cosmic puzzle strikes much closer to home, right inside our own family albums. Think of two identical twins. One decides to become an astronaut, boarding a sleek starship for a voyage to a distant star at a significant fraction of the speed of light. The other twin stays behind, living a comfortable life on Earth. When the traveling twin finally returns after what felt like a few years of ship time, they step back onto Earth to find their sibling has aged decades. The astronaut is now the younger twin. This is not science fiction, but a direct prediction of Einstein's theory of relativity. The key is time dilation, the mind-bending idea that time itself is not a universal constant ticking at the same rate for everyone. The faster you move through space, the slower time passes for you relative to someone who is stationary. For the twin on the rocket, every second, every heartbeat, every minute spent reading a book on the journey happened just a little bit slower than it did for the twin living their life back on our planet. This seems like a paradox only because our everyday experience tells us that time is absolute, a river flowing at the same speed for all of us. Yet the universe does not work that way. The resolution lies in the fact that the two twins are not in equivalent situations. The traveling twin experiences acceleration, speeding up, turning around, and slowing down, which breaks the symmetry between them. Their frames of reference are fundamentally different. This thought experiment is a powerful, personal illustration of a truth that physicists have confirmed with incredibly precise atomic clocks on fast-moving jets and satellites. Time is elastic. It stretches and contracts based on motion and gravity. The twin paradox shows us that the flow of time is a deeply personal experience, woven into the very fabric of our journey through space. But the elasticity of time opens the door to one of the most famous logical knots in all of science. You build a time machine, travel into the past, and find your own grandfather before he ever met your grandmother. In a moment of conflict or simple accident, you cause his death. This single act creates an impossible loop. If your grandfather dies before your parent is conceived, then you could never have been born. And if you were never born, you could not have traveled back in time to commit the act in the first place. So, did your grandfather live or die? The paradox pulls its own logical foundation out from under itself, leaving us with a dizzying contradiction. This is the grandfather paradox, and it is more than a science fiction plot. It is a serious challenge to the very idea of traveling backward in time within a single, unchanging timeline. The universe, it seems, has a powerful allergy to such inconsistencies. So how could time travel possibly work without unraveling reality itself? Physicists have proposed some truly mind-bending solutions. One idea is the Novikov self-consistency principle, which states that any actions you take in the past were always a part of that past. You cannot change history because you have already always been there. Your attempt to interfere would somehow be subtly guided by the cosmos to ensure events unfold exactly as they always did. Perhaps your gun jams or you slip on a banana peel at the crucial moment. The past is a locked story, and you are just playing a role that was written for you long ago. Another, even more radical solution comes from the many worlds interpretation of quantum mechanics. In this view, the moment you arrive in the past, you are not in your own history anymore. You have stepped into a new parallel timeline. In this branch of reality, you can do anything you want. You could prevent your grandfather's meeting, and a new version of history would unfold, one in which you never exist. But your original timeline remains untouched and separate, its history intact with no paradox at all. Your journey did not change the past, it merely created a new future. These ideas force us to confront the nature of cause and effect. Is the flow of time a strict one-way street, or can it fork into an infinite number of possibilities? The grandfather paradox does not just ask if we can build a time machine, it asks whether the universe would even allow it to work. If your journey into the past cannot change history without creating a logical knot, then what happens to the very idea of originality? A novelist travels back in time and hands a young William Shakespeare a leather-bound book. It contains the entire works of Hamlet, Macbeth, and Romeo and Juliet. The bard, astonished, simply copies the works and publishes them as his own, achieving everlasting fame. Centuries later, the novelist finds this same book in an antique shop and takes it back to give to Shakespeare. So, who truly wrote these plays? The book and the genius within it has no original author. It is a perfect loop, an idea that simply exists with no beginning and no end. This is the Bootstrap Paradox, a causal loop where an object or a piece of information is never actually created. it is only ever passed along its own infinite timeline. It gets its name from the absurd idea of pulling yourself up by your own bootstraps, an impossible act of self-creation. Unlike the destructive logic of the grandfather paradox, this one is about creation from nothing. The information, the object, the song, or the scientific formula is caught in an endless cycle, forever being its own cause and its own effect. The implications reach far beyond time travel stories. In quantum mechanics, some theories suggest the universe itself could be a bootstrap paradox, a self-consistent loop with no initial cause. There was no Big Bang creation from nothing, but rather a reality that has always existed because it constantly creates itself. This challenges the very core of what we consider creation and invention. Is every new idea truly new, or could it be a faint echo from a future that already exists? The Bootstrap Paradox peels back another layer of our linear experience, suggesting that time might not be a straight line but a tangled circle, where the future can write the past just as easily as the past informs the future. That same dark silence surrounding the Fermi Paradox holds another secret, written in the very emptiness of the night sky. If the universe is truly infinite and filled with an endless number of stars, then every single direction you look should eventually land on a star's surface. The entire night sky, from horizon to horizon, should be a single, blinding sheet of light, as bright as the surface of our own sun. Yet when we look up, we see a deep, velvety blackness punctuated by pinpricks of light. This is Olbers Paradox, a question that seems simple but unravels our most basic assumptions about the cosmos. The darkness above is not a default setting, it is a profound clue. The resolution lies in two fundamental truths about our universe. First, the universe is not infinitely old. It had a beginning in the Big Bang around 13.8 billion years ago. Because light travels at a finite speed, we can only see the light that has had enough time to reach us. We live inside an observable bubble, and the light from stars beyond that cosmic horizon has not arrived yet and may never will. The second reason is even more dynamic. The universe is expanding, stretching the very fabric of space. This expansion stretches the light traveling through it, shifting it to longer, redder wavelengths and sapping its energy. This cosmological redshift effectively dims the light from the most distant galaxies, turning what might have been a brilliant glare into a faint whisper we cannot see with our naked eyes. So the darkness of the night sky is not an absence of stars, but a historical record. It tells us the universe had a beginning, and that it is constantly evolving, stretching out into a future we can only glimpse in the faint, receding glow of its earliest moments. Stephen Hawking handed physics a seemingly impossible puzzle. He showed that black holes are not completely black. They slowly leak radiation, a faint whisper of energy that causes them to evaporate over trillions of years, eventually vanishing entirely. This Hawking radiation, however, appears to be completely random, a thermal static carrying no specific details about the stars, planets, or unlucky astronauts that fell in. And that is the heart of the crisis. A cornerstone of quantum mechanics states that information can never be truly destroyed. It can be scrambled, hidden, or transformed, but it must, in principle, be recoverable. Think of burning a book. The ashes seem random, but a being with godlike knowledge could reconstruct the exact arrangement of every atom, recovering every word and sentence from the smoke and debris. But if a black hole evaporates into nothing but random radiation, then the information about everything it ever consumed is erased from the universe forever. This is the information paradox, a direct conflict between the two pillars of modern physics. Einstein's general relativity, which describes the immense gravity of the black hole, seems perfectly content to let information disappear behind the event horizon, lost for all time. Yet quantum mechanics insists this is absolutely forbidden. One of these foundational theories must be wrong, or at least profoundly incomplete. The search for a solution has led to some of the most radical ideas in science. The holographic principle suggests that all the information about what fell into the black hole is not lost inside, but is instead smeared like a hologram across its two-dimensional event horizon. An astronaut falling in would see nothing unusual, but an outside observer would see their information encoded on the surface, a cosmic fossil record. Another terrifying proposal is the firewall. Perhaps the event horizon is not a gentle threshold, but a searing wall of energy that instantly incinerates anything that touches it, thus preserving information by never letting it actually enter the black hole. This idea, however, violates the principle of equivalence, another cornerstone of relativity which says free fall should feel like floating in empty space. So we are left with a maddening choice. Does information get destroyed, breaking quantum mechanics? Does it get trapped on a holographic shell, redefining the nature of space? Or is the point of no return actually a wall of fire, violating Einstein's theory? The fate of a single bit of information inside a black hole holds the key to unifying our understanding of the entire cosmos. This strange power of observation to shape reality finds its most famous and unsettling expression in a sealed box. Inside, a cat, a vial of poison, and a single radioactive atom are linked by a diabolical mechanism. If the atom decays, it triggers the release of the poison, killing the cat. If it does not, the cat lives. According to the rules of quantum mechanics, that single atom exists in a blurred state of both decayed and not decayed. Until someone opens the box to look, the entire system, including the unfortunate feline, is suspended in that blur. The cat is both alive and dead, a living paradox. This is Schrödinger's thought experiment, and it was not designed to suggest this is how the world works, but to reveal how absurd quantum theory seemed when applied to the world we see and touch. It forces a confrontation between the fuzzy, probabilistic quantum world and the sharp, definite reality of our everyday experience. The central, haunting question is this: what collapses this superposition of states into a single, solid outcome? What exactly counts as a measurement? Does the Geiger counter, by its mere mechanical operation, seal the cat's fate? Or does it require a conscious mind, a human observer, to finally look inside and, by the very act of seeing, crystallize one reality from the many possibilities? This is the measurement paradox, the unsettling idea that reality might remain in a state of potential until it is perceived. The Copenhagen interpretation, long the standard view, posits that the wave function, which describes all possible states, collapses upon measurement. But it notoriously refuses to define what a measurement is, leaving a vast, fuzzy boundary between the quantum and classical worlds. In stark contrast, the many worlds interpretation offers a breathtaking solution. It says there is no collapse. The moment the atom faces its quantum choice, the universe splits. In one branch, the atom decays and the cat dies. In another, it does not, and the cat lives. Both realities are equally real, unfolding in a vast, ever-branching multiverse. There is no paradox because every possible outcome happens, just not for the version of you in a particular branch. You open the box and in your world you find a living cat, while another you in a parallel, inaccessible world grieves a dead one. So, is the universe waiting for a conscious observer to give it form? Or are we merely passengers on an infinite tree of forking paths, each step creating new versions of ourselves and our world? The simple act of looking seems to hold a power we are only beginning to understand. While the quantum world seems indifferent to the flow of time, our own lives are defined by its relentless forward march. You can break an egg and scramble it, but you can never see those scattered pieces of shell and yolk reassemble themselves into a perfect whole. This is the paradox of time's arrow. The fundamental laws of physics, from gravity to electromagnetism, work perfectly well in reverse. If you were to watch a film of two planets orbiting each other, or two billiard balls colliding, you would be unable to tell if the film was being played forward or backward. The equations are symmetric, yet our experience of reality is utterly one way. We remember yesterday with perfect clarity, but the future is a complete mystery. We are born, we age, we never grow younger. So why does the universe have a preferred direction? The most compelling clue comes from the concept of entropy, which is a measure of disorder or randomness in a system. The second law of thermodynamics states that the total entropy of an isolated system always increases over time. A tidy room gathers dust, a hot cup of coffee cools to room temperature, and a star eventually burns out. These processes move from a state of low probability, like all the air molecules being in one corner of a room, to a state of high probability with the air spread out evenly. This relentless increase in disorder gives us the thermodynamic arrow of time, but this only pushes the mystery one step back. Why was the entropy of the universe so incredibly low in the first place? To understand this, we have to look back to the very beginning. The Big Bang represents a state of extraordinarily low entropy, a perfectly ordered and dense starting point. The universe has been unraveling, becoming more disordered ever since. Our ability to remember the past, our very consciousness, might be a direct consequence of this cosmic unfolding. We are like flotsam carried on a river flowing from order to chaos, and that flow is what we perceive as the passage of time. So the arrow of time may not be a fundamental property of the laws themselves, but a feature of our specific universe's initial conditions. We are living in the aftermath of a singular, low-entropy event, riding the wave of its inevitable dispersal. The one-way street of time is written not in the laws of physics, but in the unique and fleeting history of our cosmos. Einstein himself was deeply troubled by the implications of quantum entanglement, a phenomenon so strange he famously dismissed it as spooky action at a distance. He, along with colleagues Podolsky and Rosen, crafted a brilliant thought experiment to prove that quantum mechanics must be incomplete. They imagined a pair of particles born together, their fates forever linked. These entangled particles could be separated by any distance, sent to opposite sides of the galaxy. If you then measure a property of one particle, such as its spin, you instantly know the corresponding property of its distant partner. This connection appears to happen faster than light, seemingly shattering the cosmic speed limit that lies at the heart of relativity. For Einstein, this was unthinkable. Information simply could not travel instantaneously. He believed there must be hidden variables, unknown properties set at the moment of entanglement that predetermine the particle states, restoring a sensible, local reality where influences cannot outtrace a beam of light. For decades, this remained a philosophical debate. Then came the experiments. Physicists like John Bell devised tests to distinguish between Einstein's hidden variables and the spooky quantum version. The results were unequivocal. Time and again, the experiments confirmed that entanglement is real. The particles are genuinely connected in a way that defies our classical intuition about space. Measuring one does indeed instantly determine the state of the other, no matter the vastness between them. Yet here is the crucial twist that prevents this from being a true paradox. This instantaneous correlation cannot be used to send a message. You cannot control the random outcome of your measurement. You only know what your distant partner sees after you compare notes through a conventional, slower-than-light channel. So the cosmic speed limit remains unbroken, but our understanding of the universe is forever changed. Entanglement reveals a profound non-locality, a hidden layer of reality where things that seem separate are intimately linked. The universe is not a collection of isolated objects, but a deeply interconnected web where the very idea of a solitary, independent particle may be nothing more than a comforting illusion. This strange branching of reality offers a deeply personal and perhaps unsettling perspective on our own mortality. Imagine you agree to take part in a dangerous experiment. A gun is pointed at your head, but its trigger is linked to a quantum event like the decay of a radioactive atom. There is a 50% chance the gun will fire. From an outside perspective, the outcome is clear. In one branch of the universe, you hear a click and survive. In another, the gun fires, but what do you experience? The thought experiment of quantum immortality argues that from your own subjective point of view, you will only ever experience the branches where you continue to exist. You will always hear the click, even if the experiment is repeated 1,000 times. Your conscious awareness will seemingly follow the increasingly improbable path where you survive every single time. You would become a statistical miracle to yourself, while in countless other realities, versions of you cease to be. This is not a suggestion that you are invincible, but a logical extension of the many worlds idea. If every possible outcome happens, then your stream of consciousness is tied only to the realities where it can persist. The version of you that dies simply has no experience to report. This forces us to confront the nature of the self. Are you a single, continuous consciousness, or are you merely one thread in an infinite tapestry of possibilities? The thought experiment becomes even more bizarre when extended to natural death from old age or disease. Would an individual's consciousness always find itself in a branch where life, by some fluke, continues just a little longer, leading to a potentially endless and solitary existence in a universe where everyone else seems to perish? While this is a philosophical exercise, not a scientific theory to be tested, it stretches our understanding of identity to the breaking point. It suggests that what we consider the self might be far more fluid and fragmented than we ever imagined, a temporary constellation of experiences in a sea of infinite versions. Our own consciousness, that intimate sense of self, might be the greatest cosmic fluke of all. This unsettling idea emerges from the work of Ludwig Boltzmann, a physicist who helped us understand entropy and the arrow of time. He proposed a radical solution to the paradox of our low entropy beginnings. What if our entire ordered universe is just a rare, gigantic random fluctuation in an otherwise chaotic and eternal cosmos? In an infinitely old universe, even the most improbable events must happen eventually. Given enough time, the random jostling of atoms in a maximum state of disorder could, by pure chance, assemble a fully formed solar system, a living planet, or even a complete human brain. This is the Boltzmann brain paradox. It forces a startling statistical conclusion. In an eternal, chaotic void, it is astronomically more likely for a single, self-aware brain to spontaneously pop into existence, complete with false memories of a past and a universe that never was, than for an entire 13.8 billion year history of galaxies and stars to randomly assemble. The odds of conjuring one brain with a convincing illusion are far better than the odds of conjuring trillions of galaxies worth of ordered matter. So why do we find ourselves embedded in such a vast, coherent, and seemingly ancient cosmos? If the universe is truly eternal and random, you and I should be isolated, disembodied brains floating in a formless void, merely imagining the world we think we inhabit. The fact that we are not, that we share a consistent reality with a deep past confirmed by fossils and starlight, is profoundly strange. It suggests one of two possibilities. Either our universe is not eternal in the way that would allow for such random fluctuations to dominate, meaning it had a very specific beginning that set it on a low entropy path. Or our current understanding of statistical mechanics and cosmology is missing a fundamental piece. The Boltzmann brain paradox is a mirror held up to our own existence, questioning whether the reality we take for granted is the statistical norm or a magnificent, temporary anomaly in an endless sea of chaos. Are we the product of a grand cosmic history or just a fleeting thought in a mindless void? That unsettling question of a fragmented self finds a perfect echo in a much older puzzle about a ship. An ancient Greek hero, Theseus, sails his vessel on a long and storied voyage. Over the years, as planks rot and ropes fray, each and every part of the ship is gradually replaced. When the last original piece is swapped out, a profound question remains. Is this still the ship of Theseus? If not, at what precise point did its identity vanish? Now, launch this thought experiment into the cosmos. Imagine a generation ship, a mammoth vessel carrying human colonists on a millennia-long journey to a new star. The ship is a closed ecosystem, constantly recycling its air, water, and materials. Over centuries, every single atom, every steel plate, every wire and circuit board is replaced with matter reclaimed from waste or harvested from passing comets. The ship that arrives at its destination contains not one physical particle from the ship that left Earth. Is it the same mission? Is it the same ship? This paradox cuts even deeper when we consider the astronauts themselves. The human body is in a state of constant flux, replacing nearly every cell over a span of about 7 years. The atoms that make up your hand today are not the same atoms that were there a decade ago. An astronaut who spends a lifetime traveling between stars would be composed of entirely new material long before reaching the journey's end. So, who exactly arrives at the new world? Are they the same person who left? We cling to the idea of a continuous self, a persistent identity that rides atop this ever-changing river of atoms. But physics tells us that at the most fundamental level, we are not solid, permanent objects, but temporary patterns, swirling configurations of quantum fields. The chair you are sitting on is mostly empty space, a dance of particles that were once in distant stars. The ship of Theseus paradox forces us to ask what truly constitutes an object's identity. Is it the specific stuff it's made of, or is it the pattern, the information, the relationships between the parts? If identity lies in the pattern, then the ship remains itself even after all its parts are replaced, so long as the structure and the history are preserved. But then, what if someone collected all the discarded original planks and reassembled them into a ship? Which one is the true ship of Theseus, the one with the continuous history, or the one made of the original material? This is not just abstract philosophy. It has startling relevance to teleportation and the nature of information. If a teleporter scans your entire atomic structure, disintegrates your body, and perfectly reassembles a copy light years away, is the person who steps out the same as the person who stepped in? The pattern is identical, but the continuity of the physical substance has been broken. The copy has all your memories and believes it is you, but did you just die, only to be replaced by a perfect replica? The paradox reveals that our common-sense notion of a solid, continuous self might be a beautiful illusion, a story we tell ourselves to navigate a universe of constant, relentless change. In a cosmos where everything is flux, what are we really holding on to when we say the word I? empty space itself holds an energy so immense it should have torn the cosmos apart in its first moments. This is not a metaphor. The vacuum of space, far from being truly empty, is a seething quantum foam where virtual particles constantly flicker in and out of existence. Quantum field theory calculates the energy density of this vacuum, and the number it gives is staggering. It predicts that this vacuum energy should act as a powerful repulsive force, a cosmological constant driving an expansion of the universe so violent that galaxies, stars, and even atoms could never have formed. The cosmos would be a featureless, accelerating void. Yet when we look out at the night sky, we see a universe that is, by comparison, gently and slowly expanding. The actual measured value of the cosmological constant is not just a little smaller than the prediction, it is smaller by a factor of 1 followed by 120 zeros. This is not a small error, it is the single most inaccurate prediction in the entire history of science. Writing down the number is almost pointless. The difference is so vast it defies human comprehension. To put it in perspective, if the predicted vacuum energy were the size of the entire observable universe, the actual value we observe would be smaller than a single atom. This colossal mismatch is the vacuum catastrophe, and it points to a fundamental flaw in our understanding of reality. Something is deeply wrong. Either our theories of the quantum world are incomplete, or our understanding of gravity is flawed, or both. The tiny but non-zero value of the cosmological constant is what we call dark energy, the mysterious force accelerating the expansion of the universe today. But why is it so infinitesimally small, yet not perfectly zero? It seems as if two enormous, opposing effects are cancelling each other out with near-perfect precision, leaving behind only this faint whisper of a force. Physicists are left with a haunting question. Is this miraculous cancellation a mere cosmic coincidence, or is it a clue pointing toward a deeper law of nature, one that we have not yet discovered? The silence of empty space is not a quiet nothing, but a scream of a paradox we cannot yet decode. Even the very definition of nothing depends on who or what is asking. Picture two astronauts floating in the dark, empty void of deep space. One drifts peacefully, completely weightless, a perfect inertial observer. The other fires their rocket thrusters, accelerating steadily through the cosmos. For the first astronaut, space is exactly what it seems, a cold, silent, and utterly empty vacuum. But for the accelerating astronaut, something impossible happens. Their sensitive instruments begin to glow with heat. They detect a warm bath of particles surrounding them, a ghostly radiation that simply does not exist for their stationary companion. This is the Unruh Effect, a prediction that shatters the idea of an objective reality. The concept of a particle itself is not a fundamental building block of the universe, but a subjective experience, a story told by your own state of motion. An accelerating observer is not just moving through space, they are plowing through the quantum foam, the seething sea of virtual particles that flicker in and out of existence. From their frantic perspective, this quantum jitter gets stretched and magnified into real, detectable radiation, a heat that feels as tangible as the warmth from a fire. This creates a profound paradox. Two observers in the same patch of space-time report two completely different states of the universe. One sees nothing. The other sees a glowing fog of particles. Both are correct according to their own measurements. There is no single, true answer to the question, what is here? The resolution lies in the realization that our reality is a dialogue, not a monologue. What we call a particle is merely a particular excitation of a quantum field, and which excitations you perceive depends entirely on your path through that field. This bizarre effect is the direct conceptual cousin of Hawking radiation. A black hole's immense gravity creates an acceleration at its event horizon, and this acceleration is what makes particles appear to radiate out into space, slowly evaporating the black hole over eons. The Unruh effect suggests that gravity itself might not be a fundamental force, but rather a thermal, emergent phenomenon, a consequence of the universe's hidden, churning energy. It means that acceleration does not just change your speed, it changes the very fabric of your reality, revealing a hidden warmth to the vacuum that is forever invisible to those at rest. Crossing the event horizon should be a quiet, uneventful affair. According to Einstein's theory, if you were falling into a stellar mass black hole, you would feel nothing special as you passed that point of no return. The curvature of spacetime there is gentle, and the principle of equivalence assures you that free fall feels like floating in empty space. But to save information from being lost forever, quantum mechanics might demand a far more violent end. The Firewall Paradox proposes that the event horizon is not a silent threshold. It is a blazing wall of energy, a searing curtain of high-energy particles that would instantly incinerate any matter that comes into contact with it. Think of it not as a doorway, but as the universe's most efficient shredder, vaporizing everything into its most fundamental bits. This solves the information paradox by ensuring that information never actually falls into the black hole. Instead, it gets smeared and encoded onto this energetic surface, preserved for eternity. But this solution comes at a terrible cost. It shatters the foundation of general relativity, which insists that an observer in free fall should experience no such drama. You cannot have both a smooth spacetime continuum and a raging firewall. It is a direct, brutal conflict between our two most powerful descriptions of reality. One law must break for the other to hold, so what truly awaits at the edge of a black hole, a quiet, dark passage into the unknown, or the most violent, energetic region in the entire cosmos? The answer depends entirely on which set of rules you trust, and right now, the universe is refusing to show its hand. That searing firewall at the edge of a black hole presents a stark either-or, a brutal conflict between two sets of physical laws. But what if the conflict itself is an illusion? What if every choice, every measurement, every outcome was never truly free to begin with? This is the unsettling proposal of super-determinism, a theory so radical it questions the very foundation of scientific inquiry. It suggests that the universe is not just deterministic on a large scale, but utterly and completely so, down to the last quantum flicker. There is no spooky action at a distance, no true randomness when a radioactive atom decays, because every single event was locked into place by the initial conditions of the Big Bang. The cosmic dominoes were set up 13.8 billion years ago, and they have been falling in a perfect, unbreakable chain ever since. This elegantly resolves the paradoxes of quantum mechanics. In the Bell test experiments that confirmed entanglement, the assumption was that experimenters could freely choose how to measure the particles, but super-determinism says that choice was an illusion. The experimenter's decision, the particle's response, and the final result were all pre-linked from the dawn of time. There is no faster-than-light communication because there is no communication at all, only a single, unified, and predetermined script. The appeal is a universe of profound and perfect order, free of quantum weirdness, yet the cost is staggering. It erases the concept of free will, not as a philosophical idea, but as a physical reality. Your decision to watch this video, the thoughts you are having right now, were inevitable consequences of the state of the universe a fraction of a second after it began. It challenges the core principle of experimentation itself, which relies on the ability to make free, independent choices to test nature. If every measurement is predetermined to agree with the universe's pre-written story, how can we ever trust that we are discovering objective truths and not just reading lines from a script we had no hand in writing? We are left facing a cosmic version of ourselves in the mirror, forced to ask if the person looking back is a truly independent agent or merely an incredibly complex collection of particles executing a dance that was choreographed at the beginning of everything. Our own choices feel undeniably real, a product of conscious will, yet the cosmos might be operating on a script written at the dawn of time. This ghostly sense of a predetermined reality finds a physical counterpart in the very structure of the universe, a substance that shapes everything yet remains utterly invisible. When astronomers measure the speed of stars orbiting the outer edges of galaxies, they find something deeply wrong. According to the laws of gravity, these distant stars should be moving much more slowly, like planets on the far fringes of a solar system. Instead, they whip around at velocities that should send them flying off into intergalactic space. The only way the math works is if galaxies are embedded within enormous, massive halos of something we cannot see. This something, this ghost in the cosmic machinery, is dark matter. It does not emit, absorb, or reflect any form of light. It is completely transparent, a cosmic phantom that betrays its presence only through its immense gravitational pull. We see its effects everywhere. It bends the light from distant galaxies like a giant lens. It dictates the distribution of galaxies in vast clusters, and it provided the gravitational scaffolding for all the visible structures in the universe to form. The paradox is stark and humbling. Over 80% of the matter in the cosmos is this dark, unknown substance. It is the dominant architect of the universe's large-scale structure, the invisible hand that guides the formation of galaxies, and yet we have no definitive idea what it is made of. For decades, the leading hypothesis has been that dark matter consists of a new, undiscovered particle, something that barely interacts with normal matter except through gravity. Countless experiments deep underground have been searching for the faintest whisper of a collision between these hypothetical particles and the atoms in their detectors. So far, the silence is deafening. This persistent failure to find a direct signal has led to other, more radical ideas. Perhaps we do not need a new particle at all. Maybe our understanding of gravity itself is incomplete on the vast scales of galaxies. Modified Newtonian dynamics, or MUND, proposes that gravity behaves differently when it becomes exceptionally weak, producing the effects we mistakenly attribute to dark matter. Yet even this theory struggles to explain all the observations, particularly the way dark matter seems to clearly separate from normal matter in violent collisions between galaxy clusters. The evidence for its gravitational influence is overwhelming, but its true nature is a shadow. Is dark matter a sea of primordial black holes left over from the Big Bang? Is it a particle from a hidden sector of reality, a parallel universe brushing against our own? Every option feels like science fiction, yet one of them must be true. We are living in a universe dominated by a ghost, a silent partner whose identity remains the greatest unsolved mystery in modern cosmology. That ghostly dark matter is not the only phantom haunting our equations. A second, even more dominant shadow force is actively reshaping the entire cosmos. We have discovered that the universe is not just expanding, it is accelerating. Some mysterious repulsive force, which we call dark energy, is pushing galaxies apart at an ever-increasing rate, as if space itself is being stretched from within. This is not a gentle drift, it is a cosmic stampede. The paradox is profound. We can measure dark energy's overwhelming influence. We know it constitutes about 68% of the entire energy density of the universe, making it the single most powerful component of reality. Yet we have absolutely no idea what it actually is. The very force that dictates the ultimate fate of everything is itself a complete enigma. The simplest explanation, and the one that fits current data, is Einstein's cosmological constant, a fixed energy density inherent to the vacuum of space. But this leads us straight back to the vacuum catastrophe, that staggering mismatch between prediction and observation. If it is the cosmological constant, why is its value so impossibly small, yet not zero? The alternative is that dark energy is not constant at all. It could be a dynamic field, something that evolves over time, a cosmic cousin to the field that sparked the Big Bang's inflation. This quintessence field could be weakening or strengthening, changing the acceleration rate of the universe in ways we have not yet detected. The most radical possibility is that dark energy is not a substance or a field, but a screaming signal that our understanding of gravity, Einstein's magnificent theory of general relativity, is fundamentally wrong on the largest scales. Perhaps gravity behaves differently across the vast, empty reaches between galaxy clusters, and what we perceive as a repulsive force is just gravity showing us a new face. Each option leads to a different ultimate fate for the cosmos. A true cosmological constant points toward a cold, lonely end, where the universe expands forever into a dark, empty void, with galaxies becoming isolated islands whose lights eventually flicker out. A dynamic quintessence field could lead to a big rip, where the repulsive force grows so powerful that it tears apart galaxies, then solar systems, then planets, and finally the very atoms that constitute reality. The fact that we can even contemplate these fates, yet remain ignorant of the force that chooses between them, is a staggering reminder of our place in the cosmos. We are witnesses to the greatest show in the universe, but the director remains hidden behind a veil, its intentions completely unknown. The vast, smooth uniformity of the cosmos presents a puzzle as deep as its dark energy. When we map the faint afterglow of the Big Bang, the cosmic microwave background, we find it is almost perfectly uniform in every direction we look. The temperature is the same too, within a tiny fraction of a degree, from one horizon to the other. This tells us that the entire observable universe was once in perfect thermal equilibrium, like a room where the air has settled to a single, even temperature. But here is the paradox. According to the standard Big Bang model, these distant regions of the cosmos should have never been in contact. The universe was simply not old enough for light or heat to have traveled between them. It is as if you walked into a vast auditorium and found 1,000 people you had never met, all humming the exact same note at the exact same pitch, without any prior communication. How could such perfect coordination be possible? The leading solution is a dramatic event known as cosmic inflation. This theory proposes that a fraction of a second after the universe began, it underwent a breathtaking growth spurt, expanding faster than the speed of light for a fleeting moment. This does not violate relativity because it was space itself that was stretching. This violent inflation took a tiny, microscopic patch of the primordial universe that was already in thermal contact, a patch small enough for heat to equalize, and blew it up to a size far larger than our entire observable cosmos. What we see as opposite ends of the sky were once neighboring points in that tiny, uniform seed. The entire visible universe is just a small, homogeneous fragment of a much larger, inflated whole. Yet this brilliant solution only pushes the mystery one step further. What was the engine of this incredible expansion? What strange form of energy, a field known as the inflaton, could have powered such an event and then vanished almost without a trace? The horizon problem forces us to confront the idea that the serene uniformity we see today was forged in a firestorm of unimaginable violence, a primordial event whose true nature remains one of cosmology's greatest unsolved mysteries. That same violent cosmic inflation that solved the horizon problem also answers another, even more precise mystery about the shape of reality. The universe is flat. This is not flat like a tabletop, but flat in a geometric sense, meaning the rules of classic Euclidean geometry we learned in school apply on the grandest scales. Parallel lines never meet. The angles of a triangle always add up to 180 degrees, and space does not curve back on itself. The paradox is not that the universe is flat, but that it is flat to an almost impossibly perfect degree. For the cosmos to achieve this geometric perfection today, its initial conditions at the Big Bang had to be balanced on a razor's edge. Think of trying to balance a pencil perfectly on its tip. The slightest breath of wind, the tiniest vibration, and it topples over. Now imagine balancing that pencil not for a second, but for billions of years. The early universe faced a similar but far more extreme predicament. The expansion rate and the total density of matter and energy had to be matched with unimaginable precision. If the density had been even a tiny fraction higher, gravity would have won, pulling everything back into a catastrophic big crunch long before stars could form. If the density had been a minuscule amount lower, the universe would have expanded so rapidly that matter would have flown apart, never coalescing into galaxies or planets. The required fine-tuning is staggering. To give us the flat universe we see today, the density 1 second after the Big Bang had to be tuned to within 1 part in 10 to the power of 15. That is a precision of 0.0000000000000001%. This seems so wildly improbable that it feels like a cosmic cheat code must have been used. How could such a perfect balance occur by random chance? This is the flatness problem, and it points to a universe that was set up with impossibly perfect initial conditions. Once again, cosmic inflation provides an elegant solution. That same explosive stretching of space would have acted like a master iron, smoothing out any initial curvature. No matter how wrinkled or curved the infant universe might have been, inflating it to a colossal size would make any local curvature imperceptible, just as the surface of the Earth feels flat to us even though it is a giant sphere. Inflation naturally predicts a flat universe, forcing the cosmic density toward that critical, balanced value. The fact that our universe is so geometrically perfect is not a bizarre coincidence, but a powerful piece of evidence for a primordial growth spurt of unbelievable ferocity. The very flatness of space is a fossil, a permanent record of the universe's violent and spectacular birth. These phantom particles should be everywhere. Grand unified theories, the ambitious frameworks that attempt to merge the electromagnetic, weak, and strong nuclear forces into a single elegant rulebook, make a firm prediction. In the unimaginable heat of the very early universe, the fundamental fields should have tangled into stable defects, creating isolated north and south magnetic poles. These magnetic monopoles would be massive, incredibly dense relics, and they should be as common as protons, saturating the cosmos with their unique signature. But when we look, we find nothing. Our most sensitive detectors have scanned the depths of space and the pristine ice of the Antarctic, searching for the telltale track of a lone magnetic charge, and have come up entirely empty. This is the magnetic monopole paradox, a profound case of cosmic stage fright where a star player, confirmed by our most advanced theories, has simply failed to appear. The universe seems to have ignored a fundamental pages from its own instruction manual. Once again, the solution points back to the universe's frantic infancy. The same cosmic inflation that flattened space and smoothed its temperature would have had a dramatic effect on these primordial heavyweights, As space expanded faster than light, the density of any monopoles created before that event would have been diluted to almost zero. They were not destroyed, but scattered into the vastness of the greater cosmos, so hopelessly lost in the immense volume of the inflated universe that the chance of even a single one existing in our entire observable bubble is virtually nil. Their absence is not a failure of theory, but a stunning confirmation. The fact that we do not see monopoles is powerful, if indirect, evidence that grand unification is on the right track and that cosmic inflation truly happened. It is a brilliant demonstration that in cosmology, the things we cannot find are often the loudest clues, screaming from the emptiness about the violent, explosive birth of everything we see. A watched pot never boils, and in the bizarre world of the quantum, this old saying is a literal truth. The quantum Zeno effect reveals that the simple act of looking can trap a particle in a single state, freezing its evolution in time. Imagine a radioactive atom that is on the verge of decaying. Left unobserved, its quantum state will evolve, and it will eventually spit out a particle. But if you measure it, checking over and over again whether it has decayed, something incredible happens. Each measurement resets the atom's internal quantum clock, forcing it back to its starting point. Your constant attention effectively prevents the decay from ever happening. It is as if you are holding the atom in a state of permanent potential, a prisoner of your own gaze. This is not just a theoretical curiosity. In laboratory experiments, scientists have used rapid, repeated measurements to keep unstable particles from breaking apart, effectively using observation as a tool to control the quantum world. The implications ripple far beyond the lab, forcing us to reconsider the very nature of reality. Does this mean that consciousness, through the act of measurement, has a direct and powerful hand in shaping the physical world? The line between the observer and the observed becomes dangerously thin. At the quantum level, attention is not a passive reception of information. It is an active force, a spotlight so powerful it can stop a process in its tracks. This gives a strange new meaning to the power of the mind. If focused observation can halt the decay of an atom, what other aspects of reality might be susceptible to the influence of a conscious look? The quantum Zeno effect suggests that reality at its most fundamental level is fluid and responsive, waiting for our interaction to give it final form. It presents a cosmos where time itself can be slowed to a crawl, not by traveling at great speeds, but simply by watching intently and without interruption. Our attention can freeze a quantum particle in place, but what happens when we look for something that was never there? Lucian Hardy crafted a paradox that pushes quantum logic to its breaking point. He imagined a simple setup with two beam splitters and two paths, one for an electron and one for its antimatter twin, the positron. In most runs of the experiment, the particles go their separate ways and are detected independently. But there is a specific, rare outcome predicted by the quantum math where both detectors click, signaling that the electron and positron have met and annihilated each other. The paradox emerges when you trace the possible paths. To get that double click, the two particles must have taken specific routes that would have allowed them to meet and interact at a central beam splitter. Yet, a careful analysis of the interference patterns shows that if those specific paths were taken, the particles would have destructively interfered with themselves, making it impossible for them to have been on those paths in the first place. So how did they annihilate? It is as if two people shook hands in a room that, according to the guest list, neither of them could have possibly entered. The event happens, but the history leading up to it is logically forbidden. This is the interference of absence. Hardy's paradox reveals that quantum mechanics does not just deal in probabilities, but in overlapping, contradictory histories. The annihilation occurs through a conspiracy of possibilities. Each individual history, each potential path the particles could have taken, is impossible on its own. But when you add all these impossible histories together, their combined interference creates a new, tangible reality where the particles can meet. The universe, it seems, is not just stranger than we imagine, it is stranger than we can imagine from a classical standpoint. Our everyday logic insists that if two things interact, they must have been in the same place at the same time. Quantum mechanics calmly dismantles this assumption, showing that reality is built not on certain paths, but on a tapestry of what could be, where even impossible threads are woven into the final, measurable picture. This mathematical magic trick defies every law of physics you know. The Banach-Tarski Paradox proves that a single, solid sphere can be taken apart into just 5 pieces, and through pure mathematical manipulation, these pieces can be reassembled into 2 perfect spheres, each identical to the original. You have not added any new material, yet you have doubled the volume. It sounds like a fantasy, a violation of the most fundamental conservation laws, and in the physical world, it absolutely is. But in the abstract realm of set theory, it is an undeniable truth. The secret lies in 2 deeply strange mathematical concepts. The first is the axiom of choice, a rule that allows you to select one item from each of an infinite number of sets, even if there is no defined rule for how to make that choice. It is like being able to pluck a single, specific grain of sand from every beach in an infinite universe without any instructions. The second concept is that of non-measurable sets. The 5 pieces used in this duplication are so infinitely complex, so jagged and fractal, that they cannot be assigned a consistent volume. They are geometric ghosts, and when you shuffle these ghosts, the familiar rules of addition and conservation simply cease to apply. This paradox is a powerful metaphor that cuts to the heart of reality. Our intuition tells us that space is continuous and smooth, a seamless fabric. But Banach-Tarski suggests that this smoothness might be an illusion emerging from a deeper, more chaotic structure. In our physical world, quantum mechanics saves us from such bizarre duplication. Matter is made of discrete particles, not infinitely divisible mathematical points. You cannot carve an electron into fractal pieces, yet the paradox stands as a stark warning that our most basic assumptions about continuity, volume, and even the nature of stuff itself might be profoundly naive. It reveals that the logical foundations of the universe could be far stranger and more malleable than our everyday experience dares to suggest. The solid world around you, the phone in your hand, the very stars you see at night, might be nothing more than intricate lines of code. This is the simulation paradox, a modern argument that forces us to question the bedrock of our existence. The logic begins with a simple assumption. If an advanced civilization, far more developed than our own, could create a single, perfectly realistic simulation of a universe, then it could likely create many. Over cosmic history, countless such civilizations might arise, each running billions or trillions of simulations. The number of simulated minds living out their lives inside these digital realities would quickly dwarf the number of original, biological beings in the base reality. Now, if you are a conscious entity, you must ask which group you are more likely to belong to. Statistically, the odds are overwhelmingly against you being one of the rare, original beings. You are almost certainly living in a simulation. The implications ripple out, touching everything we think we know. The fundamental laws of physics, the constants that seem so finely tuned, might not be laws at all. They could be the initial parameters of the simulation, the rules of the game set by the programmers. The strange limits we observe, like the speed of light, could be processing speed limits, preventing the simulation from overloading. What does this say about free will? Are our choices truly our own, or are they predetermined by the algorithms of the simulation, a script we are unknowingly following? The paradox does not offer easy comfort. Some argue that any civilization with such power would likely use it for purposes we cannot imagine, or that they would have ethical qualms about creating sentient beings for a simulation. Others suggest that we might already see glitches in our reality, tiny errors in the code that manifest as quantum indeterminacy or other unexplainable phenomena. The simulation hypothesis transforms the cosmos from a physical place into a potential informational structure. It asks if we are the creators, the created, or simply data points in a cosmic computation so vast we can never perceive its edges. If conscious observation is what solidifies reality, then the early cosmos presents a profound logical loop. The universe began nearly 14 billion years ago, expanding and cooling for eons before the first stars ignited, the first planets formed, and the first life eventually blinked into awareness. According to a strict interpretation of the Copenhagen view of quantum mechanics, all of those ancient events, from the first fusion reactions in stars to the formation of Earth itself, existed only as a blur of possibilities. The cosmic wave function remained uncollapsed, a symphony of potential waiting for an audience that would not arrive for billions of years. So how did anything ever become real? This is the Observer-Induced reality paradox, a dizzying chicken and egg problem that pits the quantum rules against the very history they are trying to explain. It forces a startling question. Did the Big Bang remain in a state of quantum superposition until a conscious being finally looked back at the stars and wondered where they came from? Did our own act of cosmic inquiry somehow reach back through time and solidify the past that made us possible? This idea seems to grant consciousness a godlike power, placing human observation at the very center of cosmic history. Most physicists find this deeply unsatisfying, a return to a kind of anthropocentric arrogance that science has worked for centuries to move beyond. The search for a way out has led to other interpretations. The many worlds theory elegantly sidesteps the issue entirely by stating that every possible outcome of every quantum event does become real, just in a separate branch of reality. There was no need for an observer to collapse anything because everything that could happen did happen across an infinite multiverse. In this view, our classical-looking universe is just one thread in a vast tapestry of possibilities. Another solution suggests that a measurement does not require a human mind, but merely an interaction with any larger classical system. A stray photon bouncing off a primordial dust cloud, a particle collision in the heart of an early star. Any of these decoherence events could have performed the measurement, pinning down reality long before life emerged. Yet this only pushes the problem back. What defines a classical system? At what point does a collection of quantum particles become large enough to count as an observer? The line remains frustratingly fuzzy. This paradox ultimately drags us to the precipice where physics bleeds into philosophy. It asks what reality truly is, independent of our perception. Is the moon still there when no one is looking? Our intuition screams yes, but the most literal reading of quantum mechanics leaves the answer hauntingly uncertain. We are left staring into the abyss, wondering if our own awakening was the final piece of a puzzle the universe had been preparing since the very first moment. Even the ultimate fate of the cosmos is caught between two opposing, equally valid mathematical truths. The second law of thermodynamics paints a stark and lonely ending. As the universe expands and evolves, its energy will spread out, its temperatures will equalize, and all organized structures, from stars to life itself, will fade away. This is the heat death, a final state of maximum entropy where no more work can be done. and the cosmos becomes a cold, dark, and eternal graveyard. Yet another law, born from classical mechanics, offers a bizarre and infinite alternative. The Poincaré recurrence theorem states that any system with a finite amount of energy in a bounded space will, given enough time, eventually return to a state that is arbitrarily close to its initial configuration. If you wait long enough, all the air molecules in a room will spontaneously gather in one corner. If you wait incomprehensibly longer, every atom in the universe will eventually find its way back to a state nearly identical to the hot, dense conditions of the Big Bang. So which is it, an irreversible slide into eternal stillness, or a cosmic cycle of death and rebirth that plays out over near infinite timelines? The paradox lies in the tension between the arrow of time and the timeless, cyclical nature of the underlying equations. The heat death is the most probable state, the one the universe is overwhelmingly likely to be in. But probability is not the same as impossibility. Given an eternity, even the most improbable fluctuations become inevitable. The universe could experience a spontaneous rebirth, not through a big crunch, but through a statistical fluke of unimaginable rarity. This means the very distinction between a one-time event and a recurring cycle might dissolve over sufficiently vast timescales. Are we living in the first and only iteration of the cosmos, or are we simply one act in a play that has been performed and will be performed again an infinite number of times? The silence of the heat death may not be a final ending, but merely the long, dark intermission between cosmic encores. Plato's ancient story of prisoners chained in a cave, seeing only shadows cast by a fire and believing them to be the whole of reality, is far more than a philosophical fable. It is a perfect mirror for our own quest to understand the cosmos. Our most advanced scientific instruments, from particle colliders to space telescopes, do not show us the universe as it truly is. They show us the shadows it casts. We measure the gravitational tug of dark matter and chart the repulsive push of dark energy, but these are just silhouettes dancing on the wall of our perception. We have never touched the things themselves. The standard model of particle physics describes a zoo of quantum fields and fundamental particles, yet these are mathematical abstractions, elegant shadows that predict outcomes with stunning accuracy without revealing the true nature of the fire behind them. The paradox is that every answer we uncover only deepens the mystery, revealing new layers of shadows and reminding us of our own profound confinement. We are like the prisoner who escapes the cave, blinded at first by the sunlight of a new discovery, only to realize that the world outside is vaster and more complex than the cave dwellers could ever conceive. Our senses evolved to help us survive on the African savanna, not to perceive the 11 dimensions of string theory or the non-local connection of entangled particles. We are building a map of reality using tools that are, by their very nature, limited to tracing the outlines. So what are we truly studying? Is it the universe itself, or merely the imprint it leaves on our limited methods of detection? The allegory of the cave forces a humbling conclusion. The more perfectly our models work, the more likely it is that we are simply perfecting our description of the shadows, while the essence of reality remains forever in the light, just beyond the mouth of our cave. Your own immediate experience of this very moment feels solid and real, a definitive now. Yet physics tells us this is an illusion. In Einstein's block universe, all of time, the past, the present, and the future, is laid out in a single, frozen, four-dimensional structure. There is no universal clock ticking, no special moment that everyone can agree is the present. Your now is not my now if we are moving relative to each other. This is the paradox of the present, a deep chasm between the time we live and the time that exists in the equations. We are psychologically anchored to a moving point that physics claims does not exist. So what is this vivid, flowing present we all share? Philosophers and scientists call it the specious present, a window of awareness that feels like an instant but actually has a brief duration. It is not a single mathematical point, but a short stretch of time, perhaps 2 or 3 seconds long, that our brain stitches together into a coherent experience. You hear a melody, not a collection of isolated notes. You watch a dancer move, not a series of frozen frames. Your consciousness smooths over the gaps, creating the seamless movie of your life. But this present is specious, meaning misleading or false, because it tricks us into believing in a universal now. The conflict is absolute. Relativity shatters the idea of a single, objective present. Your present moment is just a slice through the block universe, and your slice is tilted differently from the slice of an astronaut on the moon or a spaceship moving near light speed. All those slices are equally real. The future is already out there, just as fixed and unchangeable as the past. This leaves our feeling of free will, of making choices in a flowing river of time, standing on very shaky ground. If the future is already written in the cosmic block, then our decisions are just illusions, playing out a script that was complete billions of years ago. Why would evolution gift us such a powerful, persistent feeling of a flowing present if it were not true? The answer might lie not in the laws of physics, but in the nature of consciousness itself. Our brains are prediction engines, constantly taking in sensory data and constructing a model of reality that helps us survive. The feeling of a moving present could be the user interface our mind creates to navigate a world of cause and effect. We do not experience the raw, tangled web of space-time. We experience a simplified, linear story because that is what allows us to function, to make decisions, to learn from the past and plan for a future. The block universe may be the true reality, but our conscious awareness is a necessary lie, a brilliant trick of the mind that lets us navigate a world where every moment is eternally now. That solid block universe, with its past and future eternally fixed, leads us to the final and most profound question of all. Why is there a block at all? Why does anything exist? The ultimate cosmic paradox is not about how the universe works, but that it is here in the first place. Physicists like Lawrence Krauss have proposed a compelling scientific answer, suggesting that the entire cosmos could have spontaneously emerged from a quantum vacuum. This is not a simple, empty nothingness. The quantum vacuum is a seething sea of potential, governed by the laws of quantum mechanics, where particles flicker in and out of existence all the time. In this view, our universe is just the most spectacular and long-lasting fluctuation in that eternal quantum foam. But this explanation immediately circles back on itself, creating a new layer of paradox. Is a quantum vacuum truly nothing? It has properties, it has structure, it obeys the laws of quantum physics, so we are left asking, where did those laws come from? Where did the quantum vacuum itself come from? We have simply replaced one something, the universe, with another something, a fertile vacuum governed by rules. The question of why there is something rather than nothing remains stubbornly unanswered by this scientific story. This inquiry pushes us past the boundaries of physics and into the realms of philosophy and theology. It is the final frontier of our cosmic curiosity. Some argue that the concept of absolute nothingness, a true void with no laws, no space, and no time, might be inherently unstable or even logically impossible. Perhaps something must exist by sheer necessity. Others see the existence of a universe fine-tuned for life as evidence of a deeper principle or even a creator. Yet for every proposed answer, the paradox deepens. If a god created the universe, what created the god? If the universe is one of many in a vast multiverse, what breathes fire into the multiverse? We are chasing a chain of causality that seems to have no beginning, an infinite regression that our minds cannot fully grasp. The very existence of reality, of stars, planets, and conscious beings like us who can ponder this very question, is the greatest and most beautiful paradox of all. It is the silent, stunning miracle at the heart of everything, a mystery that may forever remain just beyond the edge of human understanding. Each of these 30 cosmic riddles is a crack in the facade of our everyday reality. They reveal a universe where cats can be both alive and dead, where the past can be created by the future, and where empty space itself holds enough energy to tear everything apart. Our common sense, forged on this small, quiet planet, is completely unequipped for the true nature of the cosmos. These paradoxes are not failures of the universe, but failures of our own intuition. They are the places where our current models of physics, general relativity, and quantum mechanics reach their breaking points, screaming at each other in a language of contradictions. Yet within that conflict lies our greatest hope. Each paradox is a brilliant signpost pointing toward a deeper, more complete theory of reality. We are being guided toward a framework that must somehow marry the vast gravitational landscape of Einstein with the fuzzy, probabilistic world of the quantum. This future theory, whether it be string theory with its tiny vibrating strings, loop quantum gravity, or something we have not yet conceived, will not make the universe seem more normal. It will make it seem even more astonishing. It may require us to accept that there are more than 3 dimensions of space, or that time itself is an emergent property from a more fundamental level of reality. The very fact that we can identify these paradoxes, that we can feel the friction between our models and the truth, is a testament to human curiosity. We are the universe becoming aware of itself, and in these moments of profound confusion, we are taking our first, stumbling steps toward a truer vision of existence. The cosmos is not just stranger than we imagine, it is stranger than we can imagine, and these 30 mind-bending paradoxes are our invitation to explore that infinite wonder. Each of these 30 cosmic riddles is a crack in the facade of our everyday reality. They reveal a universe where cats can be both alive and dead, where the past can be created by the future, and where empty space itself holds enough energy to tear everything apart. Our common sense, forged on this small, quiet planet, is completely unequipped for the true nature of the cosmos. These paradoxes are not failures of the universe, but failures of our own intuition. They are the places where our current models of physics, general relativity, and quantum mechanics reach their breaking points, screaming at each other in a language of contradictions. Yet within that conflict lies our greatest hope. Each paradox is a brilliant signpost pointing toward a deeper, more complete theory of reality. We are being guided toward a framework that must somehow marry the vast gravitational landscape of Einstein with the fuzzy, probabilistic world of the quantum. This future theory, whether it be string theory with its tiny vibrating strings, loop quantum gravity, or something we have not yet conceived, will not make the universe seem more normal. It will make it seem even more astonishing. It may require us to accept that there are more than 3 dimensions of space, or that time itself is an emergent property from a more fundamental level of reality. The very fact that we can identify these paradoxes, that we can feel the friction between our models and the truth, is a testament to human curiosity. We are the universe becoming aware of itself, and in these moments of profound confusion, we are taking our first, stumbling steps toward a truer vision of existence. The cosmos is not just stranger than we imagine, It is stranger than we can imagine, and these 30 mind-bending paradoxes are our invitation to explore that infinite